Hi, it's me, Dr. Prasad Puthiyillam. Continue my classes on superconductivity. In previous class, I explained about the basics of superconductors, Josephson Effect, type 1 and type 2 superconductors. So this class is for features of superconductors or some of the important properties or behaviors shown by the superconducting materials. So one of the important features are the superconductors has three types of critical points or critical values, below which it acts as superconductors and above which it becomes a normal conducting material. In superconductors, if we increase the flow of current, then we must have to increase the critical current density, that is JC. And if critical current density is large, then the magnetic field induced is also large. So they are correlated, they are interrelated. So for an efficient use of a superconductor, the critical value need to be increased and maximum priority is given to produce superconductors with a higher critical temperature or TC. That is for practical applications, the superconductors should have a higher critical temperature. Usually low critical temperatures has limited applications, whereas the high critical temperature superconductors has got more applications. Therefore, the research focused mainly on preparing high TC materials, superconductors with a high TC or higher critical temperatures. A second important phenomena is the existence of Cooper pair. The Barden, Cooper and Schrieffer theory, BCS theory, which was created in 1957, explained the superconductivity of materials, that is explained in quantum scale. They proposed that a pair of electrons in superconductors are joined together to form a pair known as Cooper pair, which are the charge carrier containing two electrons with twice the charge of a normal electrons. If I represent schematically, when an electron or the BCS theory states that at low temperatures, a moving electron will attract nearby positive charges, distorting the crystal lattice. You can see that crystal lattice is distorted. Okay, this is called electron phonon interaction. Okay, here phonon means it is a vibration of the crystal lattice. The crystal lattice will vibrate when an electron moves through the crystal lattice. Those vibrations we call as phonon, and the electron and the interaction with the crystal lattice we call as electron phonon interaction. So when a first electron passes through this crystal lattice, it creates a higher positive charge density, which causes flow of another electron or causing another electron to draw to the region, and which follows closely near to the or closely to the first one. So these two electron pairs or these two electrons make a pair called Cooper pair, and these Cooper pairs explain the conductivity of superconductors. Not only one Cooper pair will be there in a superconductor, many such Cooper pairs will be formed, and that explains the conductivity behavior in superconductors. Okay, so here one may doubt that these electrons are having same charge. Will they repel each other? No, because of this high positive charge density, they exist as a pair that we call as the Cooper pair. The next important feature or property is known as Josephson current or Josephson effect. That means when two superconductors are separated by an insulator, Cooper pairs will tunnel from one side to the other. That is represented here. So the tunneling is represented here. From superconductor 1 to the superconductor 2, the Cooper pairs will tunnel. So the flow of electron produces a current. So this movement of electrons causes a current. That current is known as Josephson current. And the related phenomenons based on this concept, whatever phenomena based on that, though all those effects are known as Josephson effect. Persistent current. When a ring of superconducting material, a superconducting material is made as a ring, and it is kept in a magnetic field above its critical temperature, and when it is cooled to below critical temperature, then it behaves as a superconductor. Above the critical temperature, it will not behave as superconductor. So, and when even if the external magnetic field is removed, it induces or a current is induced in ring due to this self-inductance, which will continue to flow. That means a current I will start flow through the ring, and it is a continuous flow of current, which is known as persistent current. And because of the continuous movement of current, it also causes a magnetic flux B that passes through the ring. So persistent current, it is the current produced in a superconducting ring. Continuation of that, that is quantized magnetic flux and the application device which is known as SQUID. So when a magnetic flux is formed, B is formed inside that, that is represented by simplified, which is equal to N into H upon 2E, where H is the Planck's constant, E is the charge of electron, and N is an integer value 1, 2, 3, etc. That means it is in quantums or packages. Okay, so we can say that clearly here the flux it is quantized in terms of H by 2E, or the minimum value of flux associated with. If n is equal to 1, then such cases we call as fluxoid, which can be calculated as 2.07 multiplied by 10 to the power minus 15 Tesla meter square. So the magnetic flux, so defining the quantized magnetic flux, the magnetic flux that flows through the ring of a superconductor is an integral multiple of the minimum unit, or we call it as the quantum or flux quantum. Okay, so the magnetic flux which is flowing through a ring of superconductor, it is in quantum. Okay, it is a minimum unit is there. It's an integral multiple of a quantum. Okay, so this phenomenon is called a quantization of a magnetic flux. Based on the quantization of magnetic flux, or based on the principle, or we can say that when the extremely precise measurements of magnetic field is possible, we can measure even very low volumes of or quantities of magnetic field can be measured precisely by counting this quantized magnetic flux. Okay, so based on that instrument or device, that is SQUID, a superconducting quantum interference device can be constructed, which consists of a superconducting ring with one or more Josephson junctions, and it is used particularly as a sensor or a sensitive magnetometer, which capture very small changes in magnetic field, even generated with the brain or muscle move, or when the muscle move. Okay, so such devices we call it as SQUID, which is applied field of a quantized magnetic flux. So thank you very much for watching my video. I hope you understood the features of superconductors and properties of superconductor. The coming classes I'll explain in detail about the superconducting, their high temperature superconductors and other application fields. Thank you very much and have a nice day.